My name is Syram, and my partner Anton are going to be presenting our project Real-Time Machine Learning for SCADA. So in our project description, we had to create and train a neural network to ingest electrical systems data and detect anomalies and attacks. We had to maximize the prediction accuracy, use different parameter optimization methods to determine which parameters to provide for the best accurate predictions. We also had to develop an algorithm to inject attacks into data sets with a variety of parameters. And also we used hyperparameter optimization to research the best methods to predict attacks from the injected data sets. So the technologies that we used, as you can see on the screen, we used a lot. And the most important ones that we used was the random forest classifier to predict our data, the grid search and hyperpot for the parameter optimization, Panda, NumPy for data formatting, as well as data time, matplotlib for graphing, and tkinter for creating the GUI. The data sets that we were given, energy consumption, cost, and output were the three main variables that we manipulated throughout the whole project. And the parameters that are listed, we also manipulated so that we can get the highest accuracy as well as learn what is going on in the data set. Criterion is one of the parameters that we manipulated in the parameter optimization, and the two parameters that are in criterion are the gini index, which is a measure of the frequency of which an element of the data set will be mislabeled when it is randomly labeled. And in the following equation, P is the probability of the class I. Entropy is another parameter. It's a measure of information that indicates the disorder of the features with the target. In the following equation, Pi is the probability of the class I. The difference between the two are Gini is used mostly to minimize misclassification and find continuous attributes. It tends to find the largest class. Entropy is mostly used for exploratory analysis and attributes that occur in classes. It tends to find the classes that make up 50% of the data. So the two types of parameter optimizations that we did in this project, we did grid search, which extensively generates candidates from a grid of parameter values specified with the param grid parameter grid that we used. And we used another optimization technique called Bayesian optimization, which uses probability to find the minimum of the function with the goal of finding the input for the function, which can give us the lowest possible output value. It also includes the domain space, which tells us the range of input values to test by creating a probability distribution for each hyperparameter, which is listed below. We also created a attack injection algorithm to inject attacks based on the normal values of the original data set. We tested our model and hyperparameter optimization on these data sets and generated heat maps and numerical results shown in the following slides.
This is the app we developed for our project. It comes with 3 tabs: the dataset analyzer, which dynamically creates graphs based on a given dataset, and it has a variety of options; the attack injector, which creates datasets based on user-defined parameters and does all of our attack curve fitting, graphing, and saves it as a CSV file. The random forest classifier is the model that we've been using to classify the output of the data sets, and it has a lot of parameters as well that can be customized, and it also shows a heat map of in estimators and criterion, and how they relate to accuracy. All right, the first tab is the dataset analyzer, which can load any dataset, and it can show you a variety of graphs about it, like the yearly values of each time, or the hourly average, any day, any month, and energy versus cost, the energy consumption, and it can prune the duplicates for these. So I'll just show the pruned ones. Energy to cost ratio. All right, and then it can also show random forest prediction graphs for the training and test set. So here's the training set and the test set for this data set, which is our data set 3. If we look at the original data set, something you should know is the entire first half of the year are injected attacks, and these are not from our attack injector, these were just sampled. So this is the data set that all of our injected data sets are based on, and it's only based on the second half of the year. So because this data is abnormal, we trimmed it off and just used the latter part of the year to base our injection curves on. The second tab is the attack injector, which takes in a data set. The default is our original one, and it can generate a data set off of these parameters, which it will show a graph here, and the equation of the curve fits. So it curve fits the normal values for the hourly average for the entire year, which is this blue graph right here, blue line right here. And this equation corresponds to that. And then it uses these parameters to modify that line and create an attack line. So this orange line is based on an injection in points between 0 and 800. So if we look here between 0 and 800, there's a spike. It increases the attacks by about 25%. And then it's going to inject them into 80% of the days. And it's going to weight the normal value of that day by 2, and then make an average with the corresponding value on this attack curve. And then it's going to check which value is greater. And if force attacks is true, it's going to put the attack in no matter what. But if it's false and the average, the weighted average is less than the normal data point, it won't inject that attack, which helps it be realistic because no attacker would want their attack to be less than the original value. And then the seed is just for consistency in picking the random number of days, so that when we run this, we will always get the same number of days corresponding to the seed. Tab 3 is the random forest classifier. It takes a data set, the seed, training percent, number of jobs, and all these parameters for the parameter grid, and it generates a heat map comparing the number of estimators and the criterion to the accuracy. So we'll just run a small one here. It displays information before the graph comes on. Okay, so this is the heat map for that, and as you can see, the entropy is a way better predictor of accuracy than Gini, and this is also completely configurable, so we can do it with just any number of different options on a different data set, anything like that, and it'll generate a heat map for whatever we need, which is very helpful when trying to analyze if our model is doing well or not.
So our results show that based off of the injected data sets that you see, showing 45% injected attack data, 50% attack injected attack data and 55% attack data. The Bayesian optimization offered better results than using grid search in all three of the data sets. In all of the data sets that were injected by ourselves, the criterion chose gene to be the dominant parameter. Our model provided 75% accuracy with our own injected data program. And in the original data set, we went up to 90% accuracy without the data injected by us, where entropy was used as the best parameter. So the two main methods of hyperparameter optimizations that we used were the grid search and the Bayesian optimization. The grid search is represented by the heat maps, which is on the left side, and the right side is represented by the Bayesian optimization. So in the Bayesian table, we have a whole bunch of variables. The 0 represents entropy. The 1 represents gini, so we're basically comparing the two and how they work. We have three main variables that we're comparing the two criterion. The first one is precision. Precision is just the ratio of correctly predicted positive observations to the predicted positive observations. The second is recall. Recall is the ratio of correctly predicted positive observations to all observations in the actual class. And the last variable is the F1 score, which is the weighted average of the precision and recall. The score takes in both the false positives and the false negatives into account. It's in the F1 score, it's more useful than the accuracy when you have an uneven class distribution, meaning like instead of 50% data, you could have like 45%, 55%. So you look at that. To conclude the research that we did, Gini and using Bayesian optimization is better for our injected data sets, and entropy with the grid search was better for the original data set.
For our unfinished or future work, we could continue to optimize parameters to increase prediction accuracy, generate more injection data sets, and modify the injector and add the ability to put values into any prediction feature. Right now it's hard-coded as energy consumption, but we could add costs, time, stuff like that. Create data sets that are increasingly more difficult for the model to predict, more close to real life. When these attacks are injected, they're meant to be injected over a long period of time and not noticed. So we would iterate through the random forest parameters, parameter optimize it, and try and predict attacks on harder data sets. And then while doing that, we would determine which hyperparameter values have the largest effect on final prediction accuracy and optimize and find the best values for those and refine the model. Special thanks to our advisors for the project. Thank you for introducing us to it and for providing direction. And does anyone have any questions?